The Hindu goddess Kali is a thoroughly striking figure, normally depicted wearing a skirt of severed human arms and brandishing a necklace of human heads. Fitting, of course, for a goddess of destruction whose name in Sanskrit means "she who is death." But Kali is not just a destroyer, she is also a goddess of creation. Both an agent of destruction and a force of creation, I can think of no better metaphor for the next stop on our tour of the invisible universe: black holes. Black holes are the stuff of sci-fi legend. But far from being mere agents of cosmic destruction, they are also responsible for shaping the universe we live in. They are capable of swallowing vast oceans of matter, deleting stars from the universe itself, and unleashing titanic forces that shake the fabric of space and time. But they are also the sculptors of galaxies and could be the universe's final energy source in a far distant starless future. Destruction and creation. Black holes are the most extreme and most misunderstood objects in the universe. They are also very much part of the invisible universe. Dark objects with gravity so powerful that they can destroy light itself. They have baffled and challenged astronomers for a century, and even now we don't fully understand them. The quest to understand black holes will, eventually, take humanity beyond the laws of physics as we know them. In 1865, the French sci-fi author Jules Verne wrote one of the first ever accounts of a journey into space, from the Earth to the Moon. A direct route in 97 hours, 20 minutes. Better known as From the Earth to the Moon. Describes the attempt to launch 3 astronauts on a journey to the Moon using a gigantic space gun. The cannon he described, the Columbiad, was an implausibly massive construction built from 68,040 tons of iron and 400,000 pounds of explosive. Verne's goal, and the reason for inventing such an absurdly large gun, was to come up with a way of escaping Earth's gravity by achieving escape velocity. Escape velocity is a concept that dates back to Isaac Newton's initial thoughts about gravity, more than 3 centuries ago. The basic idea is this: throw a ball in the air, and it will eventually fall back down to Earth. Throw it more forcefully, and it will travel faster and higher before returning. Escape velocity is the speed that will allow the ball to overcome gravity completely and sail away forever, never to fall back down. Just a whisker slower, and it might travel very high, maybe even into space, but it will inevitably run out of steam and come crashing back. Escape velocity is the speed that allows you to slit the surly bonds of Earth. On the surface of the Earth, the escape velocity is 11,186 meters per second. This is rather fast, of course, and explains why Jules Verne needed to fire his poor astronauts out of such a massive gun. If Verne had been writing the reverse story, from the Moon to the Earth, then his characters would have had an easier time. The Moon's gravity being weaker than the Earth's, the escape velocity is far lower, at around 2.4 kilometers per second. Everything has an escape velocity, which is fairly simple to calculate. For very massive things, the escape velocity is large. To slit the surly bonds of Jupiter, you need to travel at 60 kilometers per second, more than 200,000 kilometers per hour. Conversely, for smaller things, the escape velocity can be very low. Mars's tiny moon, Deimos, has an escape velocity of just 20 kilometers per hour. A good sprinter, or anyone riding a bike, could break free from Deimos' feeble gravity and spiral off into the void, which is worth remembering next time you cycle on Deimos. The first person to imagine an object with an escape velocity so high it would be impossible to reach was the English clergyman and scientist John Michell, who has to be one of the most underrated great thinkers of all time. He spent his early life studying, teaching and researching at Cambridge, but failed to find any kind of permanent position. In his early 40s, he left Cambridge to take up a post as a church rector in a quiet Yorkshire village, where he spent the rest of his life. Throughout his career, Michell had extraordinary insight after extraordinary insight, making huge advances in areas as diverse as astronomy, geology, and the study of magnets. He was the first person to realize that earthquakes travel as waves, and that tsunami are caused by earthquakes under the ocean. He published a pioneering study which massively improved our understanding of magnetism, and invented a device for accurately measuring the mass of the Earth. It's strange and sad that he is so little remembered today. He had such a lack of interest in promoting his ideas that he never made the leap into popular imagination, despite his brilliance. The American Physical Society described him as a man so far ahead of his scientific contemporaries that his ideas languished in obscurity until they were reinvented more than a century later. John Michell's most famous idea was that of a dark star. Make anything sufficiently massive. Michell imagined a gigantic star, and the gravitational pull would become so strong that its escape velocity would be higher than the speed of light. Given that nothing can go faster than light, nothing could escape one of these dark stars. There was no need for any exotic physics either. A star made of the same stuff as the Sun, but 500 times bigger, would do it. Michell realized that one of these massive stars, with an escape velocity faster than light, would be invisible. All the light emitted by the star would be inevitably pulled back by the enormous gravity, like a thrown ball returning to Earth. He came up with this idea, eerily prescient of our modern conception of a black hole, in 1784, published in a paper with the distinctly unsnappy title, On the Means of Discovering the Distance, Magnitude, and Similar Things of the Fixed Stars, in consequence of the diminution of the velocity of their light. In case such a diminution should be found to take place in any of them, and such other data should be procured from observations, as would be farther necessary for that purpose. Even more brilliantly, Michell came up with a way that these dark stars might be found. He was the first person to discover the existence of binary stars, two stars, gravitationally bound and orbiting around each other. And Michell realized that if one member of a binary pair was a dark star, we would be able to see a single star orbiting apparent nothingness. This was the most brilliant idea he ever had, and sadly, like many of his ideas, it was so far ahead of its time, it was all but ignored by his contemporaries, and lost for 2 centuries. We have to wait well over 100 years before dark stars emerge onto the scientific stage once more. In the early decades of the 20th century, Einstein published his theory of general relativity, updating Newton's centuries-old ideas about gravity and describing a stretchy, bendy universe in which gravity is caused by the curved geometry of space and time. As physicist John Wheeler famously put it, space-time tells matter how to move. Matter tells space-time how to curve. Einstein's mathematical description of relativity comes in the form of 10 linked equations, which combine to describe how space and time warp in response to the presence of matter and energy. Einstein himself felt that this complex system of equations would never be fully solved, and he himself provided only a rough solution. He was pleased then, when just a few months later the brilliant German physicist Karl Schwarzschild managed to fully solve the equations of general relativity and perfectly describe how space would curve around a massive object. Einstein was delighted with Schwarzschild's work, saying, "I had not expected that one could formulate the exact solution of the problem in such a simple way." Schwarzschild's exact solution to Einstein's equations, however, suggested something very strange, a glitch in Einstein's elegant universe. He was the first person to realize that the laws of general relativity, in theory, allow for the existence of something called a singularity, an infinitely small point containing an infinite density of mass, where space and time themselves are crumpled into an infinitesimal speck. Unsurprisingly, This was a controversial idea. For most scientists, the concept of a singularity seemed absurd. Just because some equations predicted the existence of infinitely dense objects, made up of material compressed into a single dot of literally zero size, didn't mean such a thing actually had to exist in the real world. That would imply that you could take the mass of an entire star and cram it into a space smaller than a proton. Physicists regarded Schwarzschild's mathematics as either a bizarre trick or a sign that something had gone wrong somewhere. A divide by zero somewhere in the equations, producing a mad result that didn't correspond to anything in the real universe. Schwarzschild, however, followed the mathematics, diligently discovering the properties of these strange theoretical anomalies. He realized that the singularity itself, the impossible speck where all the numbers go to infinity, would be cut off from the universe by a boundary which he called the event horizon. The logic goes like this. At the actual singularity, the gravitational pull is infinitely strong, and the escape velocity is infinitely high. Take just a step away from the singularity, and the escape velocity will still be very, very high, but no longer infinite. As you move further and further away from the singularity, the escape velocity will decrease, because you're moving away from the source of the gravity. If you are on a platform 100 miles above the Earth, your escape velocity is lower than it would be on the Earth's surface, for the same reason. At some point, the escape velocity is going to drop below our universe's magic number 299,792 kilometers per second, the speed of light. This point, where the escape velocity equals the speed of light, is the event horizon. You can think of the event horizon as being the point of no return around a black hole. Anything inside the event horizon would technically need to travel faster than light to escape. Therefore, nothing can escape. Anything outside the event horizon, where the escape velocity is achievable, has a chance to get away. Of course, something being theoretically possible does not mean that it necessarily exists out there in the real universe. For something to exist, it's not enough to be theoretically possible. There also needs to be a way for it to form. Stars, for example, exist in the universe because they are allowed by the laws of physics, and there is an actual physical process that produces them. Gravity collapsing gas clouds, and so on. Moons made of cheese don't exist in the universe. They are allowed by the laws of physics, but there is no possible natural process that could produce one. What about singularities? Schwarzschild showed that they were technically allowed by the laws of physics, but without some actual real-world mechanism that could compress matter down to an infinitesimal point, they would remain a theoretical curiosity. The first hint that ultra-compressed material might actually exist was discovered by accident. William Herschel stumbled across a faint pair of stars in 1783, while carrying out a routine scan of the sky. The binary stars, together called 40 Eridani, seemed unremarkable at the time, and merited little more than a single mention buried in a catalogue. It wasn't until the early years of the 20th century that astronomers realized that the fainter of the two stars seemed very strange. 40 Eridani b, as it was called, was around 10,000 times fainter than the Sun, which implied was an extraordinarily tiny dwarf star. But a spectrum of the star, taken by pioneering Harvard astronomer William Mina, revealed that the little dwarf was white hot. This amount of heat, far hotter than our Sun, needed to be generated by a huge amount of mass, pressing down on the core. A back-of-the-envelope calculation suggested that a teaspoon scoop of this little star would weigh a ton. As the years rolled on, more and more of these so-called white dwarf stars were found, even though astronomers remained incredulous. The Cambridge astronomer Arthur Eddington even called them impossible stars. The central mystery was simple. How could anything become so massively compressed? The atoms and molecules that make up normal matter are held together by chemical bonds. When you try to squeeze and compress some material, it's the force of those chemical bonds that resists you. But these white dwarf stars, far more compressed and dense than anything we could make on Earth, would have shattered their chemical bonds long ago. What was going on inside white dwarfs that could make them so dense? The answer came in 1925. Austrian physicist Wolfgang Pauli came up with a theory that neatly explained the bizarre state of matter inside white dwarfs, and at the same time provided the first hint of how a singularity might be formed. Pauli's breakthrough was that electrons don't like being bunched up together in a small space. This is a result that comes from quantum mechanics, known as the exclusion principle, and says that no two electrons in a system can have exactly the same set of properties. If you take some matter and squeeze it harder and harder, first of all you're going to be resisted by the chemical bonds between the atoms. This is the resistance you feel when trying to crush a rock in your hand, for example. But if you squeeze very hard indeed, you can overcome the chemical bonds and compress the rock into a tiny ball. Pauli's exclusion principle, however, says that you can only compress something so far. It's like a much smaller scale, much stronger version of the normal chemical bond resistance that makes materials rigid in the day-to-day world. This tiny but fierce pushback from the electrons in a material is known as degeneracy pressure. White dwarfs are held up by this electron degeneracy pressure, and they are formed when stars just like the Sun die. Stars like our Sun spend their lives in a tug-of-war between forces, with gravity trying to crush the star and the pressure from starlight pushing back against the collapse. This gravity-resisting pressure is only sustained by the furnace at the center of the star, though. When a star reaches the end of its life and the nuclear fire dies, the balance of power shifts. Gravity begins to win the battle, and the core of the star gets crushed down smaller and smaller. This point, these electrons will start to push back, and this new degeneracy pressure kicks in, halting the collapse of the core. The heart of the dead star is around the size of the Earth at this point, and dense enough that a spoonful weighs a ton. The star has become a white dwarf. White dwarfs, like the star that birthed them, are also balanced at the focal point of a cosmic tug-of-war. But this time, the forces are much stronger. Gravity is still trying to crush the star down, but the combined force of all the electrons trying not to be squashed together pushes back and holds the white dwarf stable. Pauli realized, though, that the electrons pushing back against gravity could only do so much. Electron degeneracy pressure is not infinitely strong, and if gravity pushes hard enough, the balance of power shifts again. If a massive enough star dies, in other words, even the electron degeneracy pressure won't be strong enough to resist the collapse. This happens if the collapsing core is more than 1.5 times the mass of the Sun. A dead star, this massive, will crash right through the line of defense built by electron degeneracy pressure and shrink even smaller. What then? Matter has one more line of defense, one more obstacle to resist the inexorable power of gravity. Just as electrons don't like being pushed together, neutrons don't particularly get along either. Neutrons also push back when they are compressed into a small space, and this neutron degeneracy pressure is far stronger than the pushback electrons can muster. When the core of the collapsing star, having overcome the electron degeneracy pressure, reaches just a few kilometers across, the neutrons in the material start brushing up against each other. Neutrons push back against gravity hard, and this can hold the collapse of even massive stellar cores. These neutron stars, weighing more than the Sun but smaller than a city, are the most extreme objects in the universe, making even white dwarfs look fairly prosaic. A spoonful of white dwarf weighs a ton. A spoonful of neutron star would weigh as much as Mount Everest. A pencil, dropped from head height onto a neutron star, would hit the surface at 5 million kilometers per hour and land with the force of the Hiroshima nuclear bomb. For the purposes of this video, neutron stars are just the final stopping point on the way to our destination, the singularity. Neutron degeneracy pressure, which supports neutron stars against collapse, is the strongest force in the universe. But it is still finite. Pile enough matter on top of a neutron star, and gravity will eventually be victorious. Just over twice the mass of the Sun is enough to do it. At this point, even the neutrons, matter's last line of defense, are overcome, and the core of the star is crushed down smaller and smaller and smaller. At this point, there is nothing in the universe left to halt the collapse. If a star is big enough, then gravity always wins. The heart of the dead star is crushed into a point of infinitesimal nothingness. Trillions and trillions of tons contained in a volume far smaller than the head of a pin. Contained, in fact, in no volume at all. As we started this video, singularities were theoretically possible, but there was no known way for the universe actually to build one. The death of the most massive stars of all provides that crucial missing step. A way for gravity to crush the heart of a dying star into nothingness. It seems that singularities, the dark cosmic glitch hiding in Einstein's equations, might really exist after all. We didn't know it at the time, but the human race caught the first sighting of a real-life black hole in the summer of 1964. During the 1960s, astronomers had become increasingly interested in high-energy radiation from space, more invisible light, this time far off beyond the blue end of the visible spectrum. X-rays, with wavelengths around a billionth of a meter, were an all-new window to the universe. X-rays were being used for medical imaging by the end of the 19th century, but no one was able to use them to study the universe, for a reason familiar to infrared astronomers. X-rays cannot travel through our atmosphere. When an X-ray photon hits an atom, it delivers a huge packet of energy, but destroys itself in the process. From the point of view of an X-ray, the hundreds of miles of gas that lie between space and a telescope on the ground may as well be a concrete wall. The only way to detect this high-energy cosmic radiation was to get out of our atmosphere and go to space. In the New Mexico desert, in June of 1964, an Aerobee rocket equipped with a crude X-ray detector launched from the White Sands Missile Range for a brief suborbital flight. During this quick dip above the atmosphere, the rocket was able to peek, for the first time, at the X-ray sky. Time and time again, when astronomers open new windows to the universe, they find new and unexpected things. The Geiger counter attached to the Aerobee rocket picked up a powerful source of X-rays near the constellation of Cygnus, the Swan. But there was nothing particularly special in that part of the sky. Or at least, nothing that could be seen in visible light. It was too early to establish exactly where the X-rays were coming from, though. The crude early measurement could do little more than identify a source of powerful and energetic radiation, hiding somewhere within an innocuous swath of sky. Follow-up observations throughout the late 1960s narrowed down the position of this cosmic lighthouse, eventually pinpointing the source as a star, HD 226868, over 6,000 light-years from Earth. The star on its own was fairly ordinary. It was a blue supergiant, one of millions in our region of the galaxy, and certainly not capable of producing the flood of ultra-high energy radiation that seemed to be beaming from its location. X-ray radiation is produced by the same basic thermal process that makes coal dust glow in the infrared, and stars shine in visible light, just on much, much hotter scales. To glow with X-ray light, something near to this star must be heating gas up to millions of degrees. No mere star could achieve that. Astronomers didn't have to wait long for the missing piece of the puzzle. Back in the 18th century, John Michell had already predicted that his dark stars might be identified when a normal star was spotted orbiting around apparent nothingness. In 1971, Louise Webster and Paul Merton at the Royal Greenwich Observatory carried out Michel's proposed experiment. They saw exactly what the country vicar had predicted. Nearly 200 years before, the blue supergiant HDE 226868 was being pulled around by a massive unseen companion. Cygnus X1 was a binary system, consisting of a normal star and some kind of massive invisible object. And whatever that massive invisible companion was, it was an object of immense power, able to heat gas to millions of degrees and glow brightly with high-energy radiation. And at around 15 times the mass of the Sun, the invisible monster was far too big to be a neutron star. The astronomical world was convinced Cygnus X1 could only be a black hole. Einstein's impossible singularities, it seemed, were real. Cygnus X1 is also the source of one of the most famous scientific wagers of all time. In 1975, soon after the discovery that the star HDE 226868 was orbiting apparent nothingness, two of the most well-known black hole researchers, Stephen Hawking and Kip Thorne, made a bet on whether Cygnus X1 would turn out to be a black hole. Hawking bet against the idea, despite having spent much of his career working through the equations governing black holes. He described his bet against Cygnus X1's black hole nature as an insurance policy, saying, "I have done a lot of work on black holes, and it would all be wasted if it turned out that black holes do not exist." According to Hawking, he was 80% sure that black holes actually existed at the time. By 1990, the scientific case was settled. Black holes were firmly established as really existing, and Hawking conceded the bet. Stephen Hawking was a familiar face at these lunches, where anything ranging from theories about dark energy and dark matter to the earliest moments after the Big Bang was up for discussion. Stephen was not only one of the most famous researchers in the world, but also an ardent and passionate advocate for the public understanding of science. His death in 2018 was a huge loss to the scientific community. At this point, you might well be wondering how we can see black holes at all. Black holes are supposed to be these dark devourers of light. How then can they also act as beacons, with objects like Cygnus X1 blasting X-rays off so powerfully we can spot them thousands of light years away? The basic idea, in a tamer and more domesticated format, lies behind hydroelectric dams, which provide power to hundreds of millions of people around the world. The fundamental thing providing this power is gravity. Hydroelectric dams are really a way of exploiting Earth's gravitational field as an energy source. As the mass of our planet pulls water downwards, it picks up kinetic energy, which we can convert into more useful forms and use to power our lives. Black holes work in a similar way, on a much larger and much more extreme scale. Let's consider Cygnus X1, the black hole, and the ordinary star locked together in a gravitational orbit. The massive gravity of the black hole siphons off streams of gas from its blue supergiant companion. This stellar material plummets down in a waterfall of burning plasma, falling towards the black hole. Some of the gas will fall straight into the black hole, of course, never to be seen again. Black holes that are at the bottom of cosmic waterfalls of material will be surrounded by what is known as an accretion disk, dune star stuff just circling the cosmic drain before being devoured. The reason that black holes are such energetic sources of high-energy radiation is that these accretion disks spin around at a significant fraction of the speed of light. All this gas being furiously whipped around by the unmatched gravitational force of a black hole will pick up a vast amount of kinetic energy, just like an unimaginably scaled-up version of a waterfall on Earth, until the temperature in the accretion disk has reached millions or even billions of degrees. This superheated gas will glow fiercely, emitting high-energy radiation bright enough to be seen thousands of light-years away. Because the accretion disk exists outside the event horizon, this high-energy glow is free to escape the black hole and travel out into the cosmos. Black holes themselves may be invisible, but the destruction they leave in their wake makes them the brightest objects in the universe. The immense gravity of a black hole pulls a stream of star stuff from its companion, which swirls around the black hole in the form of an accretion disk. In the constellation Virgo, nestled between the bright stars Xenia and Porrima, there is a faint little star that is impossible to spot without a telescope. One of millions of similarly dim things that litter the night sky, it would have gone totally unremarked by history if it had not become the prime suspect in the hunt for a very strong source of radio waves, first spotted in the 1950s. The Radio Astronomy Group at the Cavendish Lab in Cambridge had noticed that the region of the sky near Virgo was emitting some unusually bright, long-wavelength radio waves. The British astronomer Cyril Hazard was the first person to come up with an ingenious solution: use the moon. You can wait until the moon passes over the particular patch of sky the signal comes from, and as the moon passes in front of the mysterious source, it will go quiet. Measuring the exact time that the radio signal disappears and subsequently reappears will let you pinpoint the exact location of your source. The radio waves in Virgo happen to be the 273rd entry in the third catalogue assembled by the Cambridge team. So the source was given the exciting and memorable name 3C273. Using Hazard's moon technique, 3C273 was identified as a perfectly innocuous-looking star, 100 times fainter than anything you could see with your eyes. 3C273 seemed to present a riddle. How on earth was this ordinary-looking star beaming huge quantities of long-wavelength radiation off into space? The Dutch astronomer Martin Schmidt was the first person to solve the puzzle. He used the 200-inch Hale telescope in California to take a spectrum of the strange star, hoping that the light would bring some clues to whatever strange mechanism was powering these radio waves. What he saw was extraordinary. The light from 3C273 was stretched, redshifted, by an unbelievably large amount. 3C273 was speeding away from Earth, it seemed, at the jaw-dropping velocity of 44,700 kilometers per second. In an expanding universe like ours, a faster speed means a greater distance, and the speed at which 3C273 was traveling implied it was more than 2 billion light-years away. The faint little star, it turned out, was anything but. Being more than 2 billion light-years away, but easily visible with a small backyard telescope, the star had to be a cosmic powerhouse, the likes of which we'd never seen before, 100 billion times brighter than any star and far outshining the entire Milky Way galaxy. Calculating the brightness of this star almost defied belief. If we could pick up 3C273 and place it a handful of light-years away, it would be 100 times brighter than the Sun. And, just to be clear, because this fact is so unbelievable on the face of it, this doesn't mean 100 times brighter than the Sun would be if the Sun were a few light-years away. 3C273, placed at the distance of a nearby star, would be 100 times brighter than the actual Sun. Whatever 3C273 was, it clearly wasn't a star. 3C273, complete with faint wisp, as seen by the Hubble Space Telescope. Even more strangely, astronomers watching 3C273 soon noticed something completely unexpected. The so-called quasi-stellar object, soon shortened to quasar, was changing in luminosity, dimming and brightening over the course of a few months. This only added to the mystery. Anything that varies on timescales shorter than a year has to be much, much smaller than a galaxy, no matter what its absurdly high power output suggested. The reasoning for this comes back to the speed of light. The speed of light is, of course, the fastest speed at which it's possible to send a signal. If two people are separated by 1 light hour, then it will take 1 hour for a message sent by one person to reach the other. There's no way for these people to communicate with each other on timescales shorter than an hour. In the same way, a star 1 light hour across couldn't change, get brighter. For example, in less than an hour, because one end of the star would be out of sync with the other. So, if you were to see a star pulsating on timescales shorter than an hour, you could say for certain that it was smaller than 1 light hour across. Using the same reasoning, astronomers realized that the engine powering 3C273, varying over the course of less than a year, had to be smaller than a light year across. A light year, around 1/3 of the distance between the Sun and its nearest neighbors, is a huge distance by any human standards. But it's a small space to contain a power source brighter than 100 billion stars. In 1969, the Cambridge astronomer Donald Lynden Bell made a startling prediction that the astonishingly high energy output of quasars could be explained by accretion onto a very massive black hole. Gravitational accretion onto a black hole was known to be a powerful source of energy. Think of Cygnus X1, 6,000 light-years away, lighting up the sky with X-rays. But 3C273 was something else entirely, a source of energy billions of light-years away which eclipsed the entire Milky Way galaxy. If quasars were indeed powered by accretion onto a black hole, the mass of the compact object would have to be enormous, millions or even billions of times heavier than the Sun. This was, to put it lightly, a rather esoteric idea. During the late 1960s, stellar black holes had only just made the transition from bizarre theoretical curiosity to thing that actually exists. And here was a theory that proposed the existence of supermassive black holes, hundreds of millions of times bigger than any star. Nevertheless, the argument was inescapable, and the idea caught on. The power source behind a quasar had to be both compact and extremely energetic, and virtually nothing else could generate so much energy in so tiny a space. A new species of gargantuan black holes seemed like the only explanation. Throughout the 1960s, more and more quasars were discovered. Many of them were much further away than 3C273, even lying at truly gargantuan distances that boggled the mind. Recall that seeing out to further distances means seeing further back in time. These quasars were the most distant, and therefore the most ancient, things ever seen. The quasar 3C9, discovered in 1965, has a redshift of 2, meaning the light from this quasar has been traveling across the universe for more than 10 billion years. We are seeing something which lived long before the Earth or the Sun existed. As time went on, it became clear that quasars are a lot more common in the distant universe than they are around us. Quasars, it seems, are creatures of the early universe. The glory days of the quasars came and went within the first few billion years after the Big Bang. Nowadays, in a universe nearly 14 billion years old, quasars are all but extinct. We can see them in action using our telescopes as time machines, peering back into a heroic age of the universe, where these phenomenal cosmic creatures flourished. But as the cosmos expanded and aged, the quasars dimmed. Our universe is old now, and the quasars themselves lie dormant. And dim, the fuel supply that powered them has been used up, either converted into stars or blasted into the intergalactic void. But the supermassive black holes themselves still exist, a heart of darkness in the center of every galaxy. The quasars themselves may have faded, with no more fuel falling onto the supermassive black hole to power the central engine, but we are surrounded by a universe which they sculpted. Supermassive black holes play an integral part in the evolution of galaxies, to the point where the growth of a galaxy and the growth of its central black hole can be seen as a symbiotic process. As a young galaxy grows, Great rivers of intergalactic gas flow down onto it, supplying the fuel for millions of stars to be born. Some of this gas will make its way to the central regions of the galaxy, and will eventually start accreting onto the supermassive black hole. This material falling onto the black hole switches on the powerful gravitational engine, and the galaxy lights up as a quasar. But the power output of a quasar is too much for a galaxy to contain. The staggeringly large amount of energy, billions of times brighter than the sun, blasts away the reservoir of gas. This robs the galaxy of the ability to form new stars, a process known as quenching, and even starves the black hole itself. The quasar then quiets down, the river of star fuel begins to flow again, and in time the whole process can start again. In this way, the growth of galaxies is regulated and controlled by the supermassive black hole in the center. This closely interlinked dance between supermassive black hole activity and the formation of stars is known as feedback, and is one of the most important forces to understand if we want to know why galaxies look the way they do. This work is on the cutting edge of modern astrophysics research, as both observers and theorists try to map out the intimate bond a supermassive black hole has with its host galaxy. There is one rather large problem in supermassive black hole science. How do you form a black hole that large? Forming a stellar mass black hole just takes a massive dying star, gravity, and time. Forming a supermassive black hole 1,000,000 times bigger than this is another matter. What is more, supermassive black holes form fast, very distant quasars, seen just a couple of billion years after the Big Bang, already have black holes weighing in at billions of times the mass of the Sun. Understanding how supermassive black holes form is one of the biggest puzzles in modern astrophysics. By the early 1990s, there was no reasonable doubt left in anyone's mind that black holes really existed. But as scientifically conclusive as good evidence is, it's another thing entirely to really see a strange cosmic phenomenon right before your eyes. You can have the Grand Canyon described to you all you like. Nothing will compare to actually seeing it. The exotic and extreme behavior of Cygnus X1 and active galactic nuclei couldn't really be explained as anything other than black holes. But we hadn't yet seen one of these cosmic monsters. A good place to start would be the closest supermassive black hole, Sagittarius, a star in the heart of our Milky Way galaxy. In 1995, teams of astronomers began to study the stars in the very center of the Milky Way, trying to glimpse the gravitational power of a black hole in action. Ever since the 1970s, astronomers had suspected strongly that a massive black hole lived in the center of the Milky Way. But the telescopes of the time simply weren't good enough to untangle the confusion of sources in the dense galactic core. Out in the galactic suburbs, where the solar system lives, stars are fairly thinly spread. But towards the center, the stars become more and more tightly packed, and picking individual stars out of the dense swarm that inhabits the center of our galaxy is a daunting task. The challenge was met in 1996 by a team of astronomers who spent years building an infrared camera designed specially to measure the movement of stars around the galactic center. The camera was called SHARP, the System for High Angular Resolution Infrared Pictures. Observing in the near-infrared, at a wavelength of a couple of microns, SHARP's mission statement was simple: to watch the stars in the center of our galaxy, in order to discover whether the central dark mass hiding in the heart of our galaxy was indeed a black hole. Just as astronomers can see the planets orbiting the Sun and use that to calculate the Sun's mass, based on the strength of the gravity that pulls the planets around, the SHARP team wanted to calculate the mass of the dark object in the middle of the Milky Way by tracing out the movements of the stars surrounding it. The power of the invisible infrared came into play again for these observations. the crowded and dusty center of our galaxy would be impossible to observe in visible light. The team watched these hidden central stars for years, waiting to spot the tiny shifts on the sky that would indicate that these stars were being pulled around by a supermassive black hole. Even though the stars themselves would be flying around at enormous speeds, at a distance of 25,000 light-years, the movements the team needed to pick out were tiny. Most stars moved less than 1,000th of a degree in half a decade of watching. Nevertheless, the new camera did its job, and the experiment was a success. In 1997, the team announced that they had spotted a total of 39 stars flying at hundreds of thousands of kilometers per hour around a central point. Some quick gravitational maths revealed the mass of the thing they were orbiting. The object in the center of our galaxy was several million times heavier than the Sun, but crammed into a space roughly the size of our solar system. Several million normal objects, whether they be normal stars, white dwarfs, or neutron stars, would be pretty clearly visible to our telescopes. But just like Cygnus X1, these stars were orbiting apparent nothingness. There was only one way to get several million times the mass of the Sun into such a small space, while still remaining invisible. Sagittarius, a star, the heart of our Milky Way, had to be a single supermassive black hole. In 2020, half of the Nobel Prize in Physics went to André Ghez and Reinhard Genzel, the lead scientists of two separate research groups who both helped to discover this extraordinary result. A simulation of the stars orbiting the supermassive black hole in the center of our Milky Way. In the years following this discovery, astronomers continued to watch the stars orbiting our galaxy's supermassive black hole. One particular star, S2, orbits around in just 16 years and is particularly useful for measuring the gravity around such an extreme object. In 2018, the astronomical world watched in anticipation as S2 slingshotted around the point of closest approach to the black hole. Amazingly, the star moved precisely in the way Einstein had predicted more than a century earlier. The star's orbit was shifting, tracing out a spirograph pattern that could only result from the extreme curvature of space-time around a massive black hole. Time after time, Einstein's elegant equations turn out to perfectly describe what is happening in every corner of our universe. The astronomical world was not done yet, however. Towards the end of the 2000s, an international team dreamed up one of the most ambitious projects in scientific history, to actually photograph a black hole itself. By this point, black holes were a firmly established part of the cosmic menagerie, with well over 500,000 of them recorded in sky survey catalogs. But, as National Science Foundation Director Franz Cordova put it, "We've been studying black holes for so long that sometimes it's easy to forget that none of us has ever seen one." The ambitious project was called the Event Horizon Telescope, and the aim was simply that, to take a photograph of a black hole and actually see the event horizon. A photograph like this would take black hole science to the next level, allowing astronomers to witness streams of doomed material spiraling around the cosmic plug hole at close to the speed of light, and to test general relativity by actually watching the effects of the strongest gravitational fields in the universe. Given the option of which kind of black hole to observe, the choice was clear. Only a supermassive black hole would do. The event horizon of a star-sized black hole, being just a few tens of kilometers across, would be far too small to be spotted at interstellar distances. A large supermassive black hole, on the other hand, can have an event horizon billions of kilometers across. Of course, most supermassive black holes are also much further away than stellar black holes. There are several small black holes within a few thousand light-years, but there is only one supermassive black hole, Sagittarius A star, within 1,000,000 light-years. In 2009, the 23-person team laid out their ambitious plans. Two supermassive black holes were promising candidates. Sagittarius A star in the center of our Milky Way, and the black hole at the center of the galaxy M87, around 50 million light-years away. The black hole in the center of M87, by comparison, weighs billions of times as much as the Sun, over 1,000 times heavier than Sagittarius A star. The more massive the black hole, the larger the event horizon. So M87, hosting one of the largest known supermassive black holes, was an excellent candidate despite its 50 million light-year distance. The prospect of imaging either black hole was an intimidatingly complex technological challenge. Supermassive black holes might be large on any human scale, but compared to the size of the rest of the universe, or even the galaxies that host them, they are vanishingly small. The supermassive black hole in the center of M87, for example, has an event horizon billions of kilometers across, but from our perspective on Earth, the size of the black hole on the sky would be around 100 millionth of a degree. In order to resolve an image that small, the Event Horizon Telescope would have to take a photograph equivalent to reading the lettering on a coin in New York, using a telescope in London. This isn't an exaggeration. This is, quite literally, the scale of the detail they were attempting to resolve. It was a staggering technological challenge. No single telescope was capable of achieving such detailed resolution, of course. Instead, the team relied on so-called very long baseline interferometry. Interferometry works by linking up several telescopes, allowing them to act as one big instrument. Link together two dishes a mile apart, and you can get them to act as a single mile-wide telescope, capable of finding much smaller details than either individual instrument could. Very long baseline interferometry, as its name suggests, involves linking telescopes that can be thousands of miles apart. And the Event Horizon Telescope takes that to an extreme, using a network of telescopes spanning the entire globe, including instruments in Europe, North America and Chile, and at the South Pole. The Event Horizon Telescope, in other words, built a telescope the size of the Earth. All the telescopes that joined the project were sub-millimeter instruments, designed to see the same farthest far-infrared light. Without any direct links between the telescopes, the different stations had to synchronize their measurements using GPS and atomic clocks, so accurate they only lose a single second every 100 million years. When data collection started in April 2017, the individual stations recorded well over a petabyte, 1 million gigabytes of carefully time-stamped data. Sending such a massive quantity of data over the internet would take such a long time it was faster just to get on a plane with the hard drives and fly to the data centers. Processing the mountain of data into an image took over a year. Finally, in April 2019, the team released their results, the human race's first ever sighting of a black hole. The image is both scientifically fascinating and completely beautiful, and it's no wonder it dominated newspaper headlines and social media buzz all over the world. The fuzzy glowing donut is actually superheated plasma, orbiting the very edge of the black hole at close to the speed of light. The ring is interestingly asymmetrical too, not because the black hole itself is uneven, but because of the effects of the extreme gravity. The top of the image is the near side of the black hole, made fainter as light struggles to escape the massive gravitational drag. The lower half of the image, the far side, is brightened as the warped space and time beams the light towards us here on Earth. The center of the image, though, is dark, the shadow of the black hole itself, which cuts the cosmic monster off from the rest of the universe. Larry Kimura, professor of the Hawaiian language, was invited to name the black hole. Drawing on the Hawaiian creation chant, Kumulipo, he chose the name Poe, the embellished dark source of unending creation. Given everything we know about supermassive black holes, the name is absolutely perfect. Both darkness and creation. At the time of making this video, the universe that we live in is 13.77 billion years old. Unless this video turns out to be successful beyond my wildest dreams, and you are watching these words in the year 10 million years, in which case, the universe will have ticked over an extra decimal place to become 13.78 billion years old. When we look around ourselves, it feels like we inhabit a very ancient cosmos. Even a million years is a pretty long time, and we have to look back more than 10 billion years into the past, 10,000 million years, to reach the time when quasars were active. Astronomers refer to the period between 10 and 12 billion years ago as cosmic noon, a time when quasar activity and galaxy formation were progressing at maximum speed. During cosmic noon, the starbursts were vigorous and the quasars were plentiful. Much of our research has involved measuring the amount of gas, the fuel for star formation and quasar activity, available to galaxies at cosmic noon. It turns out that there was much more of it available at early times, and this abundance fueled the intense star formation and black hole activity in the early universe. By comparison, the older universe around us feels a bit like the morning after a party. Everything is much more settled down and quiet these days. From a zoomed-out cosmic perspective, however, our current era might still count as the universe's youth. At the moment, the universe is dominated by stars. Stars produce most of the energy in the universe, and the cycle of stellar birth and death drives the evolution of galaxies. But this can't go on forever. Interstellar hydrogen is the raw fuel for star formation, and one day it will run out. There will be a time, more than 1 trillion years in the future, when the last star in the universe will be born. At this rate, it would take the current age of the universe to walk the length of a football pitch. Carry on at this speed until you've walked all the way around the planet. Once you're back at the start, take a pipette and remove a single drop of water from the Pacific Ocean. Then start walking around the Earth again, at the same 1 step per 100 million year pace. When you arrive back at the start again, take a second drop from the Pacific. 1040 years is the time it would take to drain the Pacific dry using this method. It is, in other words, a long time until black holes dominate the universe. Any intelligent life still around at this point would regard our current era almost as part of the Big Bang, the ephemeral afterglow of creation when light still existed in the universe. But even black holes don't last forever. Stephen Hawking's most famous discovery was an effect that bears his name: Hawking radiation, a means for black holes themselves to evaporate. It works like this. One result of quantum mechanics is that even empty space isn't truly empty. Virtual particles can pop into existence out of nothingness, as long as they pop out of existence again quickly. They do this by appearing as a pair, a particle and a corresponding antiparticle, which then come together and annihilate each other, balancing the universe's books, as it were. This happens all the time in a vacuum. We have measured the effect, and it's not just a mathematical trick. Now, occasionally a pair of virtual particles will pop into existence just outside the event horizon of a black hole. If this happens, it's possible for one virtual particle to be swallowed by the black hole, and for the other to escape. If this happens, the particles can't annihilate each other to balance the cosmic checkbook. The escaped particle, destined for annihilation, but granted a pardon by the black hole, carries off with it a tiny bit of the black hole's energy. Over a long enough time, the trillions of virtual particles carrying away their little packets of energy will erode the black hole down to nothing. The bigger the black hole, the longer this process takes. A stellar mass black hole will fizzle out in around 1060 years or so. After this amount of time, the only things left in the universe will be the supermassive black holes. The final era of the universe is marked by an almost endless stretch of time, while the remaining supermassive black holes get chipped away, slowly but surely, by Hawking radiation. After around 10,100 years, a span of time that defeats any equator-strolling, Pacific draining metaphor we can throw at it, the last supermassive black hole will vanish into nothingness.